In problem number 3, we've got a circular oil slick that's expanding. So let's go ahead and draw ourselves a circle, but of course remembering this is supposed to be a dynamic diagram, so that circle is increasing in size. And they're telling us that its radius is expanding at a rate of 2 meters per minute. So if that's R right there, I can tell already that the derivative that they gave us right here, the derivative of the radius taken with respect to time, is this amount right here. So that would be 2 meters per minute. Okay, so two parts to this question right now. A is asking us right here, how fast is the area of the oil slick increasing when the radius is 25 meters? So the derivative they want us to find there is the rate at which the area is growing with respect to time at the moment when, what did we say, R is 25 meters. So, I'll tell you what, I'm going to draw a line down the middle of this problem, and maybe I can fit A right here, and then eventually B on this part. Let's take a look. So we need an equation that relates radius with area of the circle. So area of a circle is pi times your radius squared. So we would differentiate both sides of that equation and get dA dt is equal to, derivative of pi r squared is going to be a 2 pi r and then a dr dt. So we're looking for the rate of change of the area when r is 25. So that dA dt then is going to be 2 times pi. The radius's time-specific value now is 25 meters, which I can put in because we've already differentiated. And multiplying that by dr dt they gave us right up here was 2. That looks like we're going to end up with a relatively nice clean answer of 100 pi, and that would be the derivative of the area with respect to t. Remember, that 25 was in meters, the 2 was in meters per minute, so if we multiply meters times meters per minute, that's going to get an answer, an area, a unit that hopefully makes sense, square meters per minute. So that's going to be our answer there for part A. All right, hopefully I've got room to do point B here, part B here as well. If the radius is 0 at time t equals 0, how fast is the area increasing after 3 minutes? So again here in part B, we still want the derivative of area with respect to time, but instead of them giving you an r value here, they've given you a t value here at the time t equals 3. So that's the big difference in part B compared to part A. So if I could somehow parlay this t equals 3 into an r value right here, then it would be very comparable to what we just did in A. Well, if the radius is 0 at t equals 0, so radius at 0 is equal to 0, we want to know where are we in 3 minutes, r of 3. Well, they've told us right here that the radius is increasing at a rate of 2 meters per minute. And since we're starting from 0, that's going to be 3 minutes at 2 meters per minute. So our radius then is going to be 6 meters at this time right over here. So now really this becomes the same problem we just did, guys. In fact, I can just jump, really, I take that back to this level right here. So dA dt then is going to be, again, still a 2 times pi. Now our radius, instead of being 25 meters, is just 6 meters at this moment, and our dr dt, the rate at which the radius is growing, is still 2. So it looks like this answer here, 2 times 2 is 4, times 6 is going to be a 24 pi, and again that'll be square meters per minute for the units for the answer for part B. So there is A and B here in problem number 3.